this chapter, we're going to be looking at powers and radicals. In this lesson, we're going to look at prime factors, greatest common factor, and the lowest common multiple.
Okay, hi everybody. So we're going to start a chapter here on powers and radicals. But where we're going to start here is we're going to take a look at prime factors, the greatest common factor, and the lowest common multiple. Okay, so, well, we need a definition to start off with here. Let's make sure that we're all aware what a prime number is. Okay, so prime number is going to be a natural number greater than 1. It's really important that we highlight that, stress that greater than 1, that is only divisible by 1 and itself. Okay, so now it's got to be greater than 1, so 1 doesn't count here. So the numbers we're looking at here are 2, 3, can't be 4 because 4 is divisible by 2, 5, 6 doesn't work because 6 is divisible by 2 and 3, 7 works, and then 8 has got more factors, 9's got more factors, so does 10, and so on and so forth. And so this is the first set of numbers here in the prime set that all have just the two factors, 1 in themselves. Okay? And interesting to note here, notice that 2 is the only even prime number. All the rest of them are going to be odd. These numbers are like the building blocks of the other numbers, the composite numbers. They're really neat, and yeah, there's lots of interesting things that we could talk about with respect to prime numbers, but we got to move on here. Now, a factors are going to be integers that divide evenly into a given number. Now, that's kind of how we're going to use this definition to start off with. That word factor can be a little bit more broad, but in terms of what we want to accomplish here, that's okay. And they can be positive or negative here. So when I look at the number 6, okay, my factors of 6 could be 2 and 3, because 2 multiplied by 3 is going to get me 6. It could also be 1 multiplied by 6, and so 1 and 6 are also going to be factors of 6. Okay? Now, let's take a look at some examples here and work through those. So to start off with here, maybe we're going to find the positive factors of, let's say, 15. Well, immediately what jumps to my mind here is 3 and 5. So 3 times 5, those are factors of 15. But we could also include 1 multiplied by 15. So we've got 4 factors of possible factors of 15 here. Let's take a look at 24. 24 is going to have a few here. We could do, let's build this up step by step here. We could do 1 times 24, but we could do 2 times 12, could be 3 times 8, could be 4 times 6. So there's a few here. 24 has got a lot of factors there. 17, on the other hand, 17 is just 1 times 17. So that's it, and that makes 17 prime. And actually, we would have known that. We saw that in the list of primes just up above there. Okay? So with that in mind, this idea of factors, and this idea of prime numbers, one thing that we can talk about are the prime factors of a given number. So what we're looking to do here is we're looking to take numbers and break them apart into the prime numbers that you multiply together to get that number. Okay? And it turns out for every number that you can look at, the prime factorization is going to be unique. And that's kind of a useful property here. Now there's a couple of different ways that we can find those prime factors of another. We can reduce a number to its prime factor identity. One way to do this is the factor tree. So what you might do here is, if we're going to look at 36, what we might do is we might say, okay, well, I know that 36 is 2 times 18. Now, 2 is a prime, so I'm just going to draw that down there. But I know that 18 can be broken up into 2 and 9. And then again, the 2's can come down here. And then I know 9 can be broken up to 3 times 3. So the prime factorization of 36, and I can't take 3 any further there, that's done, is going to be 2 times 2 times 3 times 3. Or we might say 36 is going to be 2 squared, okay, multiplied by 3 squared. Okay, that's a useful way of writing that. Now you can start that by saying, well, okay, 36, maybe you don't see the 2 times 18. Maybe instead you see the 4 times 9. And then 4 breaks down into 2 times 2. And then 9 becomes 3 times 3. And then there's my prime factors. That's just another way of getting exactly the same thing. In fact, it shouldn't matter what what tool you use, what direction you come at it from, you should end up getting the same prime factors. With a division table, what you might do with it is you might take a number, and this can be quite useful in a lot of scenarios here. And you might say, okay, 36, I know 36 is divisible by 2. And so I'm going to divide out the 2. Now, why do I start with 2? Well, 2 is the first, it's the smallest prime number. And what I do is I divide out 2 as much as I can, and then I move on to the next one, move on to the next one, until I've exhausted the possible primes that could go into some given number here. So for 36, I might say, well, I know it's divisible by 2, gets me 18. 18 is divisible by 2, that gives me 9. Now, 9 isn't divisible by 2, so I move up to the next prime. Is it divisible by 3? Yep, I get 3. And 3 is divisible by 3, and that gets me 1. And as soon as you get that 1 there, you're done. These become your prime factors. 2 times 2 times 3 times 3. Doesn't really matter how you choose to go about doing that. Okay, that's what we're looking at when we talk about prime factorization. Okay, so I'm just going to take a moment here, and then we're going to do some examples. Okay, so now the question is, determine the prime factorization for each of the following using the factorization tree. Okay, so what we're going to do is we're going to tear these guys apart here. When I take a look at 27, well, 27 is not divisible by 2. So I'm going to check, what is it divisible by? Well, I know that it's 3 times 9. Okay? 3 is a prime, so 3 is going to come down here. 9 isn't. But my factors of 9 are going to be 3 times 3. So my prime factorization of 27, now that I've got it down to just numbers that are primes, is going to be 3 cubed. Okay? I have 3 factors of 3 as 27. And that is going to be unique. There's no other number that has that prime factorization. That's going to be true for all numbers here. 144. When I look at that here, immediately what jumps out at me is this is going to be 12 times 12. Okay. Now, 12 can then be broken down into 4 times 3. 4 times 3. 3 is my prime number here, so that's good. That means that's done. But 4 can be taken down further here. That's 2 times 2, and then bring down the 3. And then that 4 can also be broken down into 2 times 2. And then we've got that 3 there. So 144 could be written as 2. Well, how many factors did I have there? 1, 2, 3, 4. So 2 to the 4 multiplied by, and how many? And I had 2 3s, so 3 squared. So the prime factorization of 144, it can be written like this, but it can also be written like that. 3,300. Now, when I look at that, the first 2 factors that just jump out at me are going to be 33 times 100. Okay? Now, 33, I like 33. I like numbers where the digits repeat like that because I suspect that there's an 11 in there, and 33 becomes 3 times 11. What's really nice about that is those are both prime numbers. So those are done. 100 can be written as 10 times 10 because it's a perfect square. So that 3 and that 11 will just come down. And then 10 can be broken up into 2 times 5, and so can that 10 right there. And so now when I list my primes, and usually when I write the primes out, I'm going to do them in order. So 2, and I've only got 2 2's there. 3, well, there's only 1 3. I've got 2 5's, though, so 5 squared. And then the last prime that I've got there is 11. So 2 squared times 3 times 5 squared multiplied by 11. That's the unique prime factorization of 3,300. Okay, now we're going to take a look at the next step here. We're going to take a look at something called the greatest common factor. And what we're referring to there is going to be the largest number that divides evenly into a set of numbers. So what it is we're looking for this building block, but we're looking for the largest building block that's a building block for each of a set of numbers here. Okay, so if that doesn't make a lot of sense, let's just take a look at a couple of examples here. We'll look at a couple of methods for solving for it, and then hopefully that will really crystallize that for you. So one way to do it, method one here, is to simply list off the factors of a given number, just like we did a few moments ago. So for example here, let's say we're looking for the greatest common factor, the largest number that is like a part of, a piece of 24 and 60. And by the way, remember when we're talking about factors here, we're referring to multiplication. So we're talking about numbers that when you multiply them together can create 24, can create 60. We're looking for the largest one that they share. So for 24, we can write out the factors pretty simply. It's going to be 1. In fact, we did that just a little while ago. 1, 2, 3, 4, 6, 8, 12, 24. For 60, and 60's got a bunch, 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, 60. And as we go through those, the largest number that's shared by both of those sets of numbers is 12. So therefore, the greatest common factor is 12. Okay? So it's the largest number that is this building block for building both 24 and 60. This is one way to do it. Another way to do it is to use prime factorization. Okay? So what we're going to do here is we're going to break up 24 and 60 into its prime factors. Now, in this case, this is already done for us. So 24 is going to be 2 times 3 times 2 times 2. So 2 cubed times 3. 60, when we break it down, is going to be 2 times 2 times 3 times 5. So 2 squared times 3 times 5. Now, so what I would do over here, this is normally how I go about doing this with students. So I've got 24 here, and I know that 24 is going to equal 2 cubed multiplied by 3. And I know that 60 is going to be 2 squared times 3 times 5. Now, I'm trying to compare these numbers so I can grab the greatest common factor. So normally what I do with this is I want the expressions, the prime expressions, to be similar in between these two so that I can compare them. And what I mean by that, and I know this is going to look a little bit goofy just for a moment, but just hold on for a second. Let me show you where I'm going with this. So notice that 60 has got 2 squared, it's got a 3, it's got 1 3 and 1 5 as a factor. 24 has got 3 2s and 1 3 as factors here. Now, to really make a good strong comparison here, I'm actually going to throw a 5 up here. Okay. Now, you might say, well, wait a minute, hold on. There is no factor of 5 in 24, and you're right. So what I'm doing is I'm going to put a 0 up there. 5 to the 0. And now that actually makes sense. You can probably see how that works, because 5 to the 0 is just going to be 1. And then 1 multiplied by 2 cubed times 3 is going to be 24. So now, when I ask you for the greatest common factor of 24 and 60, okay, the greatest common factor is going to share these prime factors. It's going to have a 2 in it, it's going to have a 3 in it, it's going to have a 5 in it. But because I'm looking for the greatest common factor, this is going to sound a little weird right now, but you're going to see a pattern here in a second. Because I'm looking for the greatest common factor, I'm going to use the lowest exponent. So what I mean by that is, take a look at this. I see a 2 cubed, a 2 squared. I'm going to use a 2 squared. And the reason is because I want the largest common factor, the factor that I can see clearly in both numbers. There isn't a 2 cubed in 60. There can't be. The largest it could be is 2 squared. Both of these, in both these cases, the 3 has an exponent of 1, so it's going to be 3 to the 1. And between the two 5s, the smallest exponent is the 0, so I'm going to put a 0 right there, which basically changes that into a 1. It kind of disappears. And so my common factor here, my greatest common factor is going to be 2 squared times 3, and that's 12. Okay? And so there you go. That's how I would go about using the prime factorization to find the greatest common factor. Now, we're going to take a look at a couple of examples to kind of help you see how that works kind of again and again. Get used to the pattern. Okay, so let's take a look at a couple of examples. So we're going to find the greatest common factor between 12 and 28, and then we're going to do it between 9, 18, and 24. First of all, we're going to use factors. Okay, so 12, when we talk about 12 here, its factors are going to be, well, let's see, 1, 2, 3, 4, not 5, 6, 8 isn't a factor, 9, 10, 11, 12, 12, there we go. So, and that makes sense here, right? 1 and 12, 2 and 6, 3 and 4. For 28, our factors are going to be 1, 2, well, not 3, 4, well, not 5, not 6, 7, and now all of a sudden we got that pair of factors there. So the next one up here is going to be 2 times 14, and then 1 times 28. The greatest common factor, the number that's this largest number that's in both of those, just slide along here, it's going to be 4. 4 is the largest one that we see in both. Now, let's go to prime factors and see if we can get the same answer there. So 12, okay, well 12, we just saw before. This is going to be 4 times 3, and we know that there are 2 2's in 4 there. So 2 squared times 3. There's my prime factorization of 12. 28 is going to be 4 times 7. I like that one because 7 is prime. And I know that 4 can be broken up into 2 and 2. So this is going to be 2 squared times 7. Now, it might be just completely obvious to you right now, and that's totally fine. And I completely appreciate that. You can jump to the answer here. But what I might do with this one is make this 2 squared times 3 to the 1 times 7 to the 0. And then down here make this 2 squared times 3 to the 0 times 7 to the 1. I'm only trying to give you guys a pattern that you can follow when the numbers get a bit bigger, a bit more ornery to handle here. This just kind of simplifies it. It makes them so that they look the same. Then when I look at my greatest common factor, that's going to be 2 times 3 times 7. Now let's think of the powers. It's going to be the lowest power here. Well, for the 2's, it's 2 and 2, so it's going to be 2. For the 3's, it's going to be 1 and 0, so it's going to be 0. And for the 7's, it's going to be 0 and 1, so it's going to be 0. And putting that together, I get a 4. That's maybe not necessary for these two numbers. But if the numbers get bigger, a little bit uglier, well, maybe that will help you think that through. Now, for 9, 18, and 24, let's take a look at the factors again. For 9, that's going to be 1, 3, and then because 9 is 3 squared, that's kind of where we turn around here, and then we got to go to 9. For 18, it'll be 1, that's divisible by 2. It's divisible by 3, but 18 is not nicely divisible by 4 or 5. It is divisible by 6, and there it is, 3 times 6. And so now it's going to be 2 times 9, 1 times 18. And then 24. Well, 24 is divisible by 1, and 2, and 3, and 4. Not divisible by 5, but 6. There it is, 4 times 6. So then 3 times 8, 2 times 12, 1 times 24. And looking through this, what's the largest number that we see in all of them? Well, look, it's got to be a 1, 3, or 9. Let's see if we can get greedy here and just grab the 9 here. I see a 9 there, a 9 there. No 9. There's no 9 in the set of factors of 24. So 3, 3, 3, and there it is. Okay, so the greatest common factor here is going to be 3. Let's take a look at that using prime factorization. So 9, well, 9 is easy. We know that 9 is going to be 3 squared. 18, its prime factorization, well, it's divisible by 2, 2 times 9, and we know that 9 is going to be 3 squared. So that's convenient. 24, okay, 24 is 3 times 8. I like 3 because it's prime, and okay, 8 is just 2 times 4, and 4 is 2 2. So this is going to be 3 2's, and then times 3 to the 1. So now making these look the same, this is going to be 2 to the 0 times 3 squared, 2 to the 1 times 3 squared, 2 cubed times 3 to the 1. So my greatest common factor is going to have those two factors in it, 2 and 3. What's the lowest factor that they have that I can see? The lowest exponent, not the factor, lowest exponent. Well, for the 2, it's going to be 0. And for the 3, it's going to be 1. And so the answer here becomes 3. It works out wonderfully. Okay, now let's take a look at the lowest common multiple, the LCM. And what we mean by that is we're looking at the smallest number that is divisible by a set of numbers. So this is the other way around. With the greatest common factor, we were looking for the largest number that divides into a set of numbers. Now we're looking for the smallest number that is divisible by a set of numbers. So in other words, in the previous one, we were looking for the building block, the largest building block for those, the numbers that we were given. Here, we are looking for the smallest number that we can build from a set of numbers, or using the numbers in a given set here. So in this case here, the number that we're looking for is actually going to be larger than typically than the numbers that we're looking at in the set, whereas with the greatest common factor, that is usually smaller than the numbers in that set. One way to do it is to simply write out the multiples. And multiples go the other direction here, right? Now we're not looking for the pieces of a number. We're looking for the number that we can build with that given number. So for example, for 3, my multiples of 3 will be 3, 6, 9, 12, 15, 18. Now, how far do I go? I don't know. I don't know where you're going to bump into it. Because multiples of 5 will be 5, 10, 15, 20, 25. I'm looking for the number that they both, the first number that both of those sets contain. Now, usually we're kind of hoping that it'll be a smaller number, but sometimes, particularly if they're both prime numbers, well, the first number you're going to get is when you multiply them together. So usually that's the largest number that I should ever have to go out to is going to be the product of those two. So that just gives you a little bit of an idea. So for example, for these guys right here, if we're going to find the least common multiple of 18, 20, and 30, I know that there is this bound to that. I know that it's not going to be any bigger than 18 times 20 times 30, but I'm hoping that I can do a lot better than that. So one way to do it is, again, to list out the multiples here. So the multiples of 18, here we go, 18, 36, 54, and so on. And I typically won't know how far I have to go. So sometimes I'll throw down a few multiples. Maybe I stop here. I try some multiples of 20 and realize, oh, wow, no, I didn't get there. So I keep writing out multiples of 18, multiples of 20 until I get the one where they overlap. I'm hoping that this is going to be a multiple of my third number as well. So I see right now that 18 and 20 are both, 180 is a multiple of both 18 and 20. Is it also a multiple of 30? Well, I throw down my multiples of 30, and yes, it is. So that's wonderful. I love the fact that worked out here. It didn't have to. I might need to go even further to find a multiple of all three. So that's one way to do it. Or you could use your prime factors, just like we were doing before here. So now I'm going to show you again, kind of off to the side, how I normally go about doing this. So with 18, my prime factors, okay, we just saw here, we're going to be 2 times 3 squared. They've done that for us. So 2 times 3 squared. 20, okay, 20 is going to be 2 squared times 5 to the 1. And 30 is going to be 2 times 3 times 5. All to the 1. Now, just like I did with the greatest common factor, I'm going to rewrite those so that I see each factor in there. So I've got 2 to the 1 multiplied by 3 squared, and I'm going to put a 5 up there, even though there is no 5 as a factor of 18. Here it's going to be 2 squared, 3 to the 0, and then 5 to the 1. 3 to the 0, remember there's no factor of 3 in 20, right to the 3 to the 0. And then it'll be 2 to the 1, 3 to the 1, times 5 to the 1. Now, my lowest common multiple is going to have all 3 of those factors that show up. But this time, okay, we're looking for the least common multiple. We're looking for the smallest number that is still bigger than the numbers that were given. So what we use here is the largest exponent. So when we look at the factor 2, I've got a 1, 2, and a 1. It's going to be 2. For the 3, I've got a 2, a 0, and a 1. It's going to be 2. And for the 5, I've got a 0 and a 1, so it's going to be 1. And 2 squared times 3 squared times 5 to the 1 is equal to 180. That's how we come up with the least common multiple. Same sort of rule as the greatest common factor, which is why I like doing it that way. It's a almost identical setup. It's just that instead of looking for the smallest exponent, now I'm looking for the largest exponent. As long as you can keep that straight, those two ideas, and keep them different in your head, you'll be fine. Okay, so let's do a couple questions here. We're going to find the lowest common multiple of each. In this first question, they want us to use multiples. So multiples of 3. What do we got here? We've got 3, 6, 9, okay, 12, 15, 18, and so on. I'm not sure if that's where I should stop here. Let's take a look at 5. Okay, 5 is going to be 5, 10, 15. Okay, well, I've got 15 there in both of them, so that's a good place to stop here. Let's just check and see what happens with the 6. Okay, so 6. Ooh, 6 is common, but not with the 5. 12. Ooh, 12 is common, but not with the 5. And then we jump right over the 15. So 15 wasn't the place to stop here. Got 18 there, but I know that I'm not going to get the 18 with the 5. So I'm going to keep going a little bit further here. So 18, what do we got here? 21, 24, 27, 30. Well, 30 is a multiple of 5. Let's see if there's anything earlier than that. 5, 10, 15, 20, 25, 30. Okay, there we go. Well, it's not looking like I'm going to get a multiple of 6 that is going to be common with 5 before 30 there. So 6, 12, 18, 24, and 30. And so there we go. The number that shows up first in all 3 of those sets is 30. So the lowest common multiple here of 3, 5, and 6 is going to be 30. Okay? That's one way of handling that particular problem. Now let's take a look at 9, 12, and 16, but we're going to use prime factors. Okay, so 9, and we've played with 9 before. We know that 9 is going to be 3 squared. 12 is another number that we've played with already. We know that's going to be 2 squared times 3 to the 1. We'll leave that in there. And then 16. You may not have played with 16, but 16 is going to be 4 times 4, and each of those 4s is going to be 2 times 2. That means we're going to have 4 factors of 2 in there. Now, to make those consistent, we're going to make this 2 to the 0 times 3 squared. Here we've got 2 squared and 3 to the 1. That works. And here we'll have 2 to the 4 times 3. There's no factor of 3 there, so 3 to the 0. So now my lowest common multiple for 9, 12, and 16 is going to have a factor of 2. It's going to have a factor of 3. But to what exponent? Well, the largest exponent that we've got here on the 2 is going to be to the 4. And the largest exponent that we've got on the 3 is going to be squared. So the number that we're looking at here is going to be 2 to the 4 times 3 squared. And that turns out to be 144. So the least common multiple of 9, 12, and 16 is going to be 144. Now let's take a look at another question here. So in this question here, we're told to find the greatest common factor and the lowest common multiple using any method. Now what I want to do is I want to kind of shove you towards the prime factorization tool here. And I'm going to show you why. You should see a pretty good reason why that might be my recommendation with these problems. But even later on in a later lesson, we're going to come back to this idea of prime factorization. So I just want you to get used to that tool. So for 20, my prime factors of 20, well, I know that 20 is 4 times 5, and 4 is 2 times 2, so it's going to be 2 squared times 5. I know that 28 is 4 times 7, that's going to be 2 squared times 7. Now I'm going to put that 7 over here because I already know that I'm going to fill in the empty factors that I don't have there so that these guys look the same. And so now my lowest common multiple for 20 and 28 is going to have a 2, a 5, and a 7 in it. But because it's the lowest common multiple, and we were just doing this, I'm going to use the largest exponent. So the largest exponent on the 2 is going to be 2, on the 5 will be 1, and on the 7 will be 1. So that's going to be 4 times 5 times 7, 2 squared times 5 times 7. And we get 140 as our lowest common multiple. Now, beautiful thing about this is that when I'm looking for the greatest common factor, I have already got it in prime. The prime factors are already set up for me. I'm already good to go. I just need to now go back and choose the smallest exponents. So the smallest exponent on the 2 is going to be the 2. That's all there is on the 2. But for the 5, it'll be 0. And for the 7, it will be 0. Okay? And so 2 squared times 5 to the 0 times 7 to the 0 is just going to be 4. And that's my greatest common factor. So once I've got the prime factor set up, it's a very easy thing for me to do. If I was to do it the other way, while I was listing the multiples and listing the factors, I would have to set up all of those lists. I'd have to have a list of factors to do the greatest common factor and then a list of multiples to have the least common multiple. But here I don't. So with 20, already done 20, I know that that's going to be, 2 squared times 5. 30, 30 is going to be 5 times 6, and 6 is going to be 2 times 3. So it's going to be 2 times 3 times 5. 50. 50 is 2 times 25. So that's going to be 2 times, and 25 will be 5 squared. Now, I can do this because I've played with these numbers quite a bit. If you're kind of still struggling to get that thing into the prime factorization, that is okay. If it takes you a little bit longer, that's not a problem. Okay? As long as we get you there. Now let's write these out with space for every factor. So I need a 2, a 3, and a 5. A 2, a 3, and a 5. A 2, a 3, and a 5. And it's in the exponents that I really identify what's going on. So this is going to be 2 squared, 3 to the 0, because there is no 3, 5 to the 1. 2 to the 1, 3 to the 1, 5 to the 1. 2 to the 1. Again, there's no 3 here, so 3 to 0, 5 squared. So my lowest common multiple of 20, 30, and 50 is going to have a 2, a 3, a 5 in it. And this time, because it's the lowest common multiple, we are looking at the largest exponent. So that's going to be a 2, a 1, and a 2. So what do we got here? That's going to be 4 times 3 times 25. So the least common multiple is going to be 300. The greatest common factor of 20, 30, and 50 is also going to have those 3 factors in it, but it's those exponents that we're looking at here. Now we're looking for the smallest exponent. So on the 2, it's going to be a 1. On the 3, it'll be a 0. And on the 5, it'll be a 1. So it really amounts to just 2 times 1 times 5, or 10. And there's my greatest common factor. So that's how I would encourage you to go about doing that. It's not the only way to do it. It's maybe not even necessarily always the best way to do it. Okay? But you're going to see some consistency in the work that's expected in the rest of the curriculum here. Anyway, now let's take a look at some other problems. Okay, so let's take a look at some word problems here. And it says for word problems, we're going to use the following hints, just so that we can figure out what tool it is we're going to use here. So typically when you see the word maximum, greatest, biggest, largest in a word problem, that's about these 2 ideas. Well, we're going to use the greatest common factor. Now, on the other hand, if you're using minimum, least, lowest, or smallest, those are your hints that you're looking for the lowest common multiple. Okay, so let's take a look at a problem here. It says, use a tile that measures 16 by 40 centimeters. Okay, what is the side length of the smallest square bathroom floor that can be covered? So we're going to use this piece to cover a larger area, but we're interested in the smallest of those areas that we can cover with that. So that is a lowest common multiple question here. Now, let's take a look at we could probably list off the multiples of 16 and 40 and get the answer really quickly here, but I really kind of want to push this prime factor thing here. So I know that 16 is going to be 2 times 8, which is 2 times 4, which is going to be 2 times 2. So I know that 16 is going to be 2 to the 4. 40 is going to be, well, it's going to be 8 times 5, which is going to be 2 times 2 times 2, 2 cubed times 5. Okay? So remember, to match those up here, I'm going to put a 5 up here to the 0, because there is no 5 as a factor of 16. And there's one 5 that's a factor of 40. So my lowest common multiple here of 16 and 40 is going to have a 2 factor in it and a 5 factor in it. And because we're looking for the lowest common multiple, I'm going to use the largest exponent. So it's going to be 4 on the 2 and 1 on the 5. And when I take a quick look at that, okay, that is going to be 16 times 5, which is 80. So what's the side length of the smallest square bathroom floor? 80 centimeters, which is a pretty small bathroom. Anyway, let's move on. A kitchen that measures 440 inches by 168 inches is being tiled. What is the side length of the largest square tile that could be used? So now we're looking for the other way here. Now we've got the larger dimension, and I want to go back to the smaller piece that filled it in. And I want to know what is that largest of those smaller pieces that can be used. Well, because we got that word largest in here, that's going to be, greatest common factor question. So let's take 440 and rip it apart into its prime factors. Well, I know that 440, is going to be divisible by 2. That's going to be 2 times 220. And that's going to be divisible by 2, which will be 110, which is divisible by 2. And that gets me 55. Okay, and I'm just kind of running that through on my calculator over here, just so you can see how I'm doing that. So 440 divided by 2, divided by 2, divided by 2. And now I'm stuck with 55, but I know that 55 is going to be 5 times 11. And so my prime factorization here is going to be 2 cubed times 5 to the 1 times 11 to the 1. Now let's take a look at 168. Okay, 168. Let's just run it through here. So first of all, I know that's divisible by 2. I know 84 is divisible by 2. I know 42 is divisible by 2. And I can tell right now, there's my 3 2's, my 3 factors of 2, and I tell right now that 21 is not divisible by 2. That is, 21 is going to be 3 times 7. And so what we've got here is we've got 2 cubed, well, that's nice, times 3 times 7 to the 1. Okay, so what I want to do here is I want to include all of my factors here. So I'm going to rewrite this. And the more comfortable you get with this, the less of this kind of work you need to do, quite honestly. I mean, you'll be able to just jump to these answers here really quickly here. But this has got to have a 2 in it, a 3, a 5, a 7, and an 11. So 3 2's, no 3's, 1 5, no 7's, 1 11. 2, 3, 5, 7, 11, 3 2's, 1 3, no 5's, 1 7, no 11's. So my greatest common factor here of 440 and 168 is going to be, and remember, we're still using the same factor, so 2, 3, 5, 7, 11. But this time we're only going to use the smallest of the exponents there. So on the 2's, well, that's still going to be just a 3. On the 3, it'll be 0. On the 5, it's a 0. On the 7, it's a 0. And on the 11, it's a 0. So this is going to be 8 times 1 times 1 times 1 times 1. Or just 8. The greatest common factor of those two numbers is going to be 8, which means we're looking at a square whose side length is 8 inches. One more. Okay, Tara ran around the track in 5 minutes. Todd in 6 minutes, and Taylor in 8 minutes. Now, if they start at the same time, when will they meet at the same starting point again? In other words, When is the first time that they all meet up again after going around at their different rates at the starting line? So what we're looking for here, and it's not stated here, but you got to think through the problem a little bit. I'm asking you for the shortest time when this occurs. Okay, that's the implication here. Okay, when is that first time, that shortest time where that event is going to occur? And because of that, that implies we're looking for the lowest common multiple of these numbers here. Now, 5, if I break it apart into its prime factors, is 5. 6, if I break it apart to its prime factors, is going to be 2 times 3. And 8, if I break it apart into its prime factors, and we've already seen this, is going to be 2 cubed. So if I put all those factors there, and again, like I said before, the more comfortable you get with this, the less you have to worry about little details like this. You can kind of skip right over these guys. 2 cubed, and this will be 3 to the 0, 5 to the 0. Okay. The lowest common multiple, I was going to say greatest common factor there, but no, that's what I meant. Lowest common multiple of 5, 6, and 8 is going to have a 2, a 3, and a 5 in it to the largest exponents that we see. So here it's going to be 2 cubed. Here it's going to be 3 to the 1 and 5 to the 1. Okay? And so now we are going to get 2 cubed is 8 times 3 is going to be 24 times 5. That will get you 120. So when will they all meet together at the starting line again? After 120 minutes.